Hello everyone. Let's try this way of doing our course. Well, this is our first module. We're going to look at rabbits and foxes. It's continuing our look at population growth. So here is our island. On the island we've got 2,000 rabbits, and we're trying to figure out what's happening to the rabbit population. We've seen how unconstrained growth is an unrealistic model and seen how logistic growth is more realistic because it takes into account the carrying capacity, i.e. the limited resources that you have in your environment. But there's other things for our rabbits to worry about, diseases, parasites, other herbivores who are going to compete for resources, plus predators, and that's what we're going to look at. We're going to add foxes to our model, and we're going to basically assume that vegetation, space, and water are not going to restrict our rabbits, and that the foxes are going to be the main thing which is going to impinge on, which is going to restrict the rabbit population. And we're going to assume that the rabbits are the main food supply on the foxes, and so that's going to be the main driving force behind the fox population. Okay, so here are our assumptions. So without foxes, the rabbits are going to grow logistically. Without rabbits, the foxes are going to decay exponentially. The foxes are going to kill rabbits, and so each fox is going to eat a fixed proportion of the total rabbit population in any time period. And for the foxes, each mother fox will convert a fixed proportion of the rabbit population into new foxes, into babies. Okay, so now these are these assumptions turned into mathematical formulas. So for the rabbits, we have the logistic equation. For the foxes, we have exponential decay. This is in the absence of the other species. But with foxes, for the rabbits, we're going to subtract A times RF, where A is some constant. And so remember, R times F is the number of interactions between rabbits and foxes, the number of theoretical maximum number of interactions. And so there's going to be some proportion of those which are going to occur in any given time period. And of those encounters, only a certain number are going to lead to the foxes actually successfully hunting the rabbits. And so for the foxes, we add the component B times RF. So again, RF, R times F is the total number of rabbit-fox interactions, and some of those are going to be converted into rabbit kills, and then you need a certain number of rabbit kills to turn that into a baby fox, and of course only a certain proportion of the foxes are possible have the ability to make baby foxes, i.e. the mother foxes. So putting that all together, we get those Lotka-Volterra equations with bounded growth, which you see up the top there. And so if you go now and open Lotka Excel file, you'll see the following model implemented. So I've just chosen what I thought were reasonable values for the parameters. Main thing is we're starting with 2,000 rabbits and 10 foxes. And on the next slide, you'll see a graph of what happens with this model. Okay, so we see some waves, and we can maybe think about why that happens biologically, because what would happen was it seems that we start off with lots of rabbits, and so that drives up the fox population, and as there's more foxes, that drives down the rabbit population, and that in turn causes the fox population to go down, and that's going to cause the rabbit population to go up. So you can kind of see why there might be some kind of wave pattern happening there. So notice that I plotted 100F rather than F. So I multiplied the fox population by 100 because there are just so many fewer foxes than rabbits. So I just multiplied by 100 so you could actually just see the waves of the fox population that happens. We see that the most that the rabbit population can be is just a little bit below 4,000. So it's well short of the 10,000 carrying capacity. And the peak fox population is around 35. Remember, we have to divide by 100 to get the actual fox population. So the question I want you to look at is, on the next couple of slides, I gave different initial fox populations, 5, then 20. And I want you to try for yourself an initial fox population of 50 and see what effect these changes have on the rabbit population. So in particular, do we still see that wave motion, which then kind of dies out and seems to settle on a particular value? What is the peak rabbit population? And what is the length of time between those peaks? And how does that change as we change the initial number of foxes? Okay, here it is with initial fox population of 5. We see maybe something kind of similar to what we saw in the first slide. And here we see what happens when there's initial fox population of 20. Again, we seem to see similar kind of behavior. Okay, let's look at a slightly different model. Since we're assuming that there are no constraints upon the rabbits besides the foxes, let's get rid of the logistic part of the equation. So if you do that, you get the original Lotka-Volterra model, which was developed by them in the 1920s. And so here are our new equations for our island. So I want you to modify your Excel file to get this. So all you have to do is change the R prime column by getting rid of that factor. Remember, it's the 1 minus R divided by C factor. So to get rid of that, and you'll get this new model, and you should see what you see on the next slide. Okay, so we're seeing different from before, right? It doesn't seem to be dying out that way. We're definitely getting some kind of periodic behavior right here. And again, you know, the rabbits go up, makes the foxes go up, and that makes the rabbits go down, and that makes the foxes go down, and we get this kind of nice cycle. Okay, so the peak rabbit population still seems to be just below 4,000, but the peak fox population is now much greater, it's around 80. And the main difference is, as I said, we have that periodic behavior. There's no settling in on a stable population. And the period seems to be around 80 months. Okay, so I want you to repeat what we did on the first model with this. Look at the next two slides, which have initial fox populations of 5 and 20, and then do it for yourself for 50. And again, see what effects different initial fox populations have on the rabbit population. In particular, are we still seeing periodic? What is the peak rabbit population? And what about the period, the length of the interval between those peaks? Okay, so actually we do seem to have nice periodic behavior here, but different peaks and different periods maybe. And here it is for initial population of foxes of 20. Okay, so after this, what I'd like you to do is just to send me the answers to those two questions that are in the module there. That is just for, just to show that you've done the module. I'm not going to grade it for accuracy. The main thing you want to see is that you actually gone ahead and done this module. And then there'll be a couple of homework questions which will be due at the typical time. Okay, hope that all was pretty clear. Thank you.